Good morning. We're looking at the last bit of rotational kinematics. That's going to be what is the rotational kinetic energy and how we can link it to the linear kinetic energy and to everything else that we did. So far what we have seen is what the angular position, angular displacement, velocity, and acceleration are and what their definition. We also saw what the links in between the linear and rotational variables are, the linear variables and the rotational variables here, tangential acceleration, radial acceleration. We also saw the special case of constant angular acceleration and how we can write that. Let's take a look again at this. So I have here the reference line, and I will try to rotate this cup with respect to this black X here. This is where I want the axis of rotation to be. I have three different points in blue, in green, and in red. Blue being the closest to the axis, green in the middle, and red the furthest away. So when I rotate this cup, or when it rotates for some reason, what we have is this. It rotates, and it rotates, and it rotates, and it rotates. And it rotates and keeps rotating, hopefully around the same axis of rotation, and if not, well, imagine that that axis of rotation is static. Imagine then that it keeps rotating. What we saw is that these 3 points in the same span of time did the same angular displacement but different linear displacement, because not the same. They are not at the same radial distance from the axis of rotation. Because they're not at the same distance from the axis of rotation, they will not have the same tangential speed. So they will not have the same kinetic energy. If you isolate this point and consider its small mass, and this point and its small mass, and this point and its small mass, they will all have 3 different kinetic energies, even if they're moving in a circle at a constant angular speed with a constant angular displacement in the same time. Considering that they have different kinetic energies because they have different tangential speeds, how can we find the overall kinetic energy of all of this? You can imagine that every point of this cup is at a different distance from the axis of rotation, so every point will have a different kinetic energy. All that we need to do really is take this cup, split it into very, very, very tiny pieces, so small that we can consider them to be points. We calculate the kinetic energy of each of those points and we take the big sum. If we have only 3 different points, that's easy enough. We have a sum of 3 terms. We have infinitely many points. It becomes more complicated. And as often, there's a shortcut. This is the kinetic energy, the linear kinetic energy for one point or one object whose mass can be concentrated at its center of mass. If we have more than one object, what we do, or more than one point, what we must do to find the total kinetic energy of just those 3 points is take the sum. The kinetic energy of the blue point is 1/2 the mass of the blue point times its speed squared. The kinetic energy of the green point is the 1/2 times the mass of the green point times its speed squared, and the same for the red. The total kinetic energy is just the sum. And that's if we only have 3 points. What if we have many, many more? Well, we keep going. We take the sum of the kinetic energy of the first point, plus the second point, plus that of the third, and the fourth, and the fifth, and so on, up until we reach the nth, big N point, that is the final particle of the whole cup. So we can rewrite this, the sum for all the points. Now, remember, we have a link in between the linear speed of every point that is different for every point to the angular velocity, the angular speed of the object. That's the same for every point. So let's use this definition. The individual speed of the point is its individual radius times the common angular speed. So we can replace this in here and rewrite everything like so. And this will be your kinetic energy, considering the common angular speed, all of the masses of all of the points and all of their distances from the axis of rotation, and the factor 1/2 that stems from the kinetic energy. But that's cumbersome, so let's do a small final step. I'll define a quantity that I'll call the moment of inertia, and its symbol is going to be capital I, and its value is going to be the sum of the product of the mass times the distance to the axis of rotation squared of all of the points of the object. And then we can rewrite the kinetic energy like so. We then have the updated version, if you wish, of the two kinetics energy. If an object has purely rotational linear motion, it has linear kinetic energy, 1/2 mv squared. If an object has only rotational motion, angular motion, it has only rotational kinetic energy, k sub ROT for rotation, is 1/2 I omega squared. The kinetic energy in either case is a factor 1/2 times the inertial property of the object times its speed squared. The inertial property, m or I, is a characteristic of the object, and it tells you how hard it will be to make the object either move linearly or move angularly, if angularly is a word. The units of the moment of inertia are kilograms meters squared times meters squared. And that's it. The units of the rotational kinetic energy are joules, like they are for the linear kinetic energy. Finding this moment of inertia is difficult for a number of objects. Take this marker. Relatively simple. It has just this small handle, but otherwise it's somewhat a cylinder, right? But not quite, because it's empty for some bits that's covered by the cap. Or take my mug. CLS, very nice facility out in Saskatoon. Brightest light in Canada is what they advertise, but it's true. But take my mug. Has a handle, so some mass on the outside. It's empty inside unless there's water. Calculating the moment of inertia is difficult for any objects, and we need integrals and we need calculus, and it becomes a mess. So in the notes, you have a table that summarizes some moments of inertia for different objects that you'll have and that you'll encounter in the problems. And you have all of these also in the formula sheet. You don't need to learn any of those by heart. You can just use that table as a reference. I forgot to mention something about the moment of inertia earlier, and that is the very important fact. So the moment of inertia depends on the mass of the object, of every point, but also, and more importantly, because of the square, where that mass is. You can have two objects, for example, these two balls, that have the same mass. Because this one has stuff that is further away from the axis of rotation, assume it's straight through the center here. Because this one has stuff that is further away from the axis of rotation than the turquoise one, it has a bigger moment of inertia. Even if the two balls have the same mass and it's as tough or as easy to make them move linearly, this one will be tougher to rotate than this one because of the different sizes. And this goes for every object, and that is also why it's tough to calculate the moment of inertia of a weird object, for example. First, we need to define where the axis of rotation is with respect to this. So for a ball or a sphere, that's easier. If the axis of rotation passes through the center of the thing, its center of mass, then it's the same regardless of where it is and where the axis is and what's the rotation. For this, it's different. If the axis of rotation passes straight through vertically like this and the clothes hanger rotates like this, it's easier to rotate because most of the mass is concentrated right here, along very close to the axis of rotation. If the axis of rotation vertical, but we switch it here, so that it rotates like this, for example, around the hook, then it's tougher to rotate. Now, it's somewhat light, so it's easy for us humans, but when you have something that's bigger and bulkier, it becomes more difficult. And then, again, if the axis is vertical, here we have these two clamps. They're very far away. There's a lot of mass that is far from the axis of rotation, so the moment of inertia is bigger than if these two were here. And of course, this would be an intermediate state and everything else in between. And then if you have a lot of mass hanging on one side like this, you have an even bigger moment of inertia because all of this is very far from the center of rotation and this is heavy. It would be even bigger the moment of inertia if I had another thing like this on this side. But like this, much smaller because all of the same mass is much closer to the axis of rotation. That's really the big thing. The moment of inertia is a kind of weird quantity, much like many things in rotation. It depends on the mass, but also where that mass is distributed. If you look at my mug, a weird object, the moment of inertia will be different whether the axis of rotation is through the center here of the mug vertically, the mug rotates like this, or if the axis of rotation is right here and the mug rotates like this around, so the handle and the bowl of the mug are at opposite directions around the axis and rotate like this. And that's why we have the table in the notes in part 9 with different objects, different standard objects that we'll consider in our problems and their moments of inertia. Because I don't want you to do this, and I don't want you to do this for what's called an extended object, which is an object that has all of its points so close together that they're essentially touching. The real form of the moment of inertia is this, or the extended version from the initial point, the first point to the final point. The final bit that we can do is link the work to the rotational kinetic energy. And that's simply by remembering that a work is just a change of kinetic energy. That's what a work is or does to an object. That's the link in between the two. Whether that's linear kinetic energy or rotational kinetic energy, it doesn't really matter. It will still be the same thing. Now, if it is rotational kinetic energy, we can find the work done by the force that caused that rotation, but we don't know how exactly rotational motion is done. That's in the next chapter. That's in part 10. So I'll leave you with this, and I'll see you then.